Hello everyone, it's noon time. Let's actually get started. Today, let's see. Let me check my microphone. Hello? 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 Okay. Okay. So far we have been covering different programming paradigms. So in our course, the chapter 1, we had the introduction. And then after that, chapter 2 and chapter 3, we are on memory model and data type. So these are basic language issues. And then we go into the chapter 4 to this chapter 9. Okay, these different lectures. Lecture 4 to lecture 9. I think it's like chapter 3 or 4 to chapter 7. Okay. Anyway, this portion we are on different programming paradigm. We cover the so-called imperative programming paradigm, functional programming paradigm, object-oriented programming paradigm. So now we are going to go to the lecture 10. That is the last unit that we have. That actually is language and translation. So first we talk about the general language issues, and then we talk about different programming paradigm and the language to support those different programming paradigm. Now we go into the unit of the language translation. Okay, language translation. So language translation is from one language we translate to the other language. Okay. And then they are supposed to have another unit that actually on the machine code. Okay. So that would be the hardware issue of the programming language. But in this course, we do not cover it. Okay. So you can look at the textbook for those issues. And usually those are included in the course of the compiler course, or it will be included in the course of a computer architectural course. Okay. But here we focus more on the language translation. So there is some student questioning like, okay, what kind of the term project I can work on? Let me repeat one more time. Okay, the term project, we accept any projects. Okay, we accept any project as long as it's related to programming language. So what project we consider to be related to programming language course? Anything that actually involve language translation. So anything that involve language translation means that you translate from A language to B language. That is one kind of the translation. You translate from high-level language to low-level language. That's one kind of language translation. You translate from text to graphics or graphic to text. That's also language translation. Okay, so basically anything involve language translation will be acceptable. Okay. If you work on something else, say some students suggest that, may I work on game design? Of course not. That's not our course topic. You work on the game design, then that's not really related to our course. And some say that, may I work on some topic in data science? No, of course not. It's really just data science itself. It's not related to our course. Machine learning, no, it's actually machine learning that is related to our programming language. So the minimum requirement for the term project is you must actually work on something that involve language translation. That's the minimum requirement that you need to have. So programming language course, our course is on programming languages pragmatic. That's actually the mechanism for programming language. So the minimum requirement is your project must involve language translation. If your project doesn't involve language translation, then we don't accept it. Okay, we don't accept it. Okay, these are on the term project. That means I'm just repeating one more time. Okay, we will get started for tokenization. Okay, so starting from this chapter 8, okay, this is lecture 10. We are on language translation. So that is from A language to B language, from high level language to low level language, or sometimes from text to graphics, or from graphic to text. Okay, so these are the basics of the translation. So when we do language translation, there are a few steps. The first step is called lexical analysis. And this lexical analysis involving the tokenization. So tokenization, what is tokenization? Tokenization is that you do have some word. Let's assume that you have some word. Okay, let's assume you have some words. So basically, okay, so these are different words that you have. So let's assume that this is the language that actually you send to the language translator. So you want to tokenize. So these are different tokens. So a token is similar to a word. Okay, so sometimes you may have, I haven't. I didn't. Okay. So this kind of word, you still want to actually create a token for this. So there are certain rules that actually this is considered to be a token. Those rules, we call it lexical rules. Okay, so lexical rule is the rule that actually define your tokens. And different language may have different lexical rules. Okay, so if you have 1,000, actually, I'm sorry, TH, okay. Then you have to know about why this is a word. That's the lexical word you may have. So the same text in English and the same text used for math, they may have different lexical rules. Okay, but you have to base on the lexical rule to determine what is a word, what is not. But sometimes you may have like 10 rules. You have semicolon, but this semicolon is considered to be a separate token to the 10 rules, the rules and 10, and actually different token. Okay. Sometimes semicolon may belong to one of the tokens. So it actually depends on what you look at. Okay. What kind of language you have. You look at Java, there's one lexical rule. You look at C++, there's one lexical rule. Different language have different lexical rule. But tokenization is based on the lexical rule to generate your words. Okay, so that's the first step for lexical analysis. You based on the input that you have to create your words. Let me clean this out. So that's the first step. Second step is that you do get that different let's see, you do get the different words. So you do get tokens. So these tokens may have different grammar rule. So we talk about syntax analysis. So that's the second step. Step stage based on what you have. So this one we tokenize it as I, and that is a pronouns. And this have, we tokenize as have, and that actually is a verb. Okay, something like that. So each term may have its grammatical positions. And then based on those grammatical positions, we can organize, create a syntax like, okay, you have the pronouns, verb, object, and then this one is the verb, the verbal phrase. Okay, so these are the grammatical structure of this sentence. So based on this grammatical sentence, okay, that's the second step. You actually do syntax analysis. And from the syntax analysis, you do language translation. So that's the back end of your compiler. Okay. So basically, this tokenization is the first step of your compilation. And sometimes when you do AI, that's the same thing. Tokenization is also the first step for the AI, because AI sometimes is text to graphic or graphic to graphic as a generative AI. Okay, so these are translation AI or generative AI. You do translate from one language to the other. That actually you depend on the first stage tokenization as well. Okay, so that's the meaning of the tokenization. So that including you need to read and write file access and then understand what are the I mean, these are not syntax diagram, but it actually is on the lexical rules. Okay, but the diagram itself is called SDD, okay, syntax diagram. And then you write the regular expression. Regular is to the language to define the lexical rules. Okay, so these are the topics that involved in this tokenization. So this chapter is basically on lexical rules and how to write regular expression to define the lexical rules, and then talk about how to use the regular expression in the tokenization. Okay, these are the topics that we cover this week. So overall, tokenization is a common task for data scientists, for AI, for machine learning. Tokenization is also in the first step, and actually, in AI, they count a lot of tokens. Okay, a lot of tokens. You base on the tokens to process your AI. Okay, so most natural language processing project have tokenization as its own first step, because the foundation of developing good models and understand what the kind of text we have, and using statistical database to match the best rules to process it. Okay. So text processing is for the lexical analysis. There are standard steps. So you recognize the language class. So first you recognize it's a Java or it's a English or it's a C++. You analyze the language class. That's not hard to understand because usually the language have some keywords. Okay. And then you actually analyzing the data structure, document structure, the segment, the title, the paragraph, the functions, the arrays, okay, those kind of the document structure class, okay. And then you actually break into tokens using the rules, the lexical rule to break them onto tokens. So you have if parentheses a double equal sign 3, it will be broken down into 1 token, 2 token, 3 token, 4 token, 5 token, SIG tokens. Okay, those are the tokens that you would have from Java language. Okay, so that actually is the next thing you would do. And then you do the monetization, stemming, morphological analysis. That's actually more advanced analysis on the language. Okay. And then you store the inverted index. That's your verb, pronouns, those different index. Okay, so lexical analysis is the process of converting a sequence of characters into a sequence of tokens. And this is the so-called sequence. Sometimes we call it string. So your C double plus usually include IO string, F string, okay, file string, S string, okay. So those are the input sequence, file sequence or string sequence, okay. So that's actually also involve tokenization. So a program that actually perform the lexical analysis called lexical analyzer, sometimes called lexer or scanner, okay. So basically where you would use the tokenization, that is natural language processing, text mining, okay, data mining, machine learning and AI, information retrieval, search engine. Okay, these are different locations you would need to use the tokenization. So you do tokenization, you break down the sentence into tokens. Okay. And then after that, you do syntax analysis. You call a parsers. Okay, later. So basic indexing pipeline, you have the words, you do tokenization, you use the linguistic module, okay, and then you have the friend, Roman, and countryman. You start to create embodied index. Then maybe the factorization of the words, maybe is the tense words, okay, or the pronouns words, and then maybe is some other labeling, you are labeling the text as well, okay. So if you are graphics, you actually you label it as car, a person, or a certain region of the image. Okay, you label them. And then here you are, if you are using text, this one friend maybe is a nouns, maybe a person or people, okay. And then you actually created another keyword, maybe relationship. Okay, those are some label that related to this word. So you do image processing or you do a computer vision, same thing, you create car, and then you may actually create another label for vehicle. So when you do reasoning, the vehicle words will be used for the different linguistic module to do reasoning, to find the rules for you. Okay, so indexing is also very important. So this whole thing from creating the tokens to creating the labels, okay, these different things is all included in the basic indexing pipelining, okay. So you have a source code or a file, you actually do lexical analysis to create tokens. And based on the tokens and the structure of the tokens, you actually create grammatical analysis. But sometimes the grammatical position also determine the lexical word should be, which, so for example, I haven't. So this one actually is a verb. So since you find out it's a verb and it actually may have a abbreviation, so you will change the rule for the lexical analysis as well. So it won't be lexicalized as have an N and then a quote and then T. Okay, it won't be lexicalized into 4 different tokens. Instead, it will be lexicalized into 1 tokens. Okay, so that you still need to depend on your context to determine, sometimes determine the lexical rule. Okay, so this is what this chart say. And then based on that, you create an abstract syntax tree. Okay, so basically on your word, and you say this one is a sentence, and the sentence break down as subject, verb, object. And subject, you can have nouns, pronouns, okay, whatever. So those are the abstract syntax tree that you created. So your text is again put into certain parsing tree. Okay, because we want to deal with the parsing tree. So early when we are talking about functional programming, we also talk about recursion on tree. So recursion on tree is a basic operations when you actually try to parse the tree. Okay, that's actually very important. So right here, we start to talk about programming language and language translation. And then you will see the pieces that we used before now become an important concept. Okay, so you build a tree and then you start to use your traversal on the tree to generate the target language. So you convert it from high level language to machine code. Okay, so that actually is your interpreter to do interpretation. Okay, so these are the basic structure of a compiler. So our course is programming language. So programming is basically defining the grammatical structure and lexical structure. Okay, and up to here, usually it's the front end of the compiler, and back end, the language translation. The machine code generation is actually is the compiler course. Okay, so here talk about another structure for the compiler. Okay. And always there is a symbol table. Okay, symbol table. So basically, this symbol table is that when you I have $300. So this one already put into the symbol table is the I, and then you label it as verb, and then as first person. Okay, so creating a few label for this word. Heaven, you actually created as I'm sorry, I is actually a nouns, pronouns. Okay, sorry. And heaven is actually becoming labeled as verb. Okay, whatever. So that's the symbol table. Symbol table is used later when you need to use the parser to analyze the syntax. Okay, so here we actually talk about the importance of the tokenization. And then there are many packages that you can use for tokenizers. So you can directly use the split function in Python language. Okay, that actually is a brute force design, but usually complicated grammar cannot be implemented. So that's only for very basic tokenization. And then you can use a regular expression, and regular expression is in C++. They do have regular expression. You can use Python. Python also have the regular expression module. Java also have regular expression module. Okay, so most of the language do have the regular expression, and you can use them. And you can also use the natural language toolkits. Okay, and LTK. That's in Python. Okay, you can use some commercial rule, Keras. Okay, Spacey. Okay, different tools to do tokenization. So different tools come with different complexity, and then can deal with different level of difficulty on the tokenization. Okay. So here, this one is the example. Okay, token. Okay, whatever. And sometimes you need to deal with the capital. Okay. Positive case or not. So usually dash packer should it be considered one token or token in different position. This may be, you may get a different answer. For example, you consider there are two primary name, that would be two token. But if you are talking about a company, that actually is one word. So whether the Hewlett Packard is one word or two words, that depend on the grammar. Okay. So if you say Hewlett Packard is a great company, then this is, of course, this purely paper word is one single token is actually announced. But if you say Hewlett dash Packard are two great families. So in this situation, it would be considered two different words. So basically, your grammar sometimes your syntax, I'm sorry, your lexical rule sometimes may change. Okay, depending on the context. So first one, we talk about the tokenization by split function. Okay, so here it show you how you do read in a file using the read function will convert the whole file into one single string. And that one single string you do stripping. Okay. So this one is read in the whole file. And then you do split after it. Okay, and then you create this different one. So this one apparently sometimes the dot minus these are actually included into the token. But this may not be what we want. Okay, so sometimes you need to do pre-processing before you feed it into the split function. And then you can also do line by line tokenization. So you read in a line at a time. So previous one, you read in the whole file once. Okay, here you actually do read in line by line. Okay, this is the line by line read in. And then you do split on the lines. So same thing, you create almost the same tokens. And then you can also do character by character read in, okay, word by word read in, okay. Okay, anyway, but now next one is that for the tokenizer design, you need to use the regular expression. And then from the regular expression, you convert it to NDFA, okay, non-deterministic finite automata, okay. And from the automata, you do minimization to reduce the number of steps and make the scanner design easier to do. Okay, so the whole purpose is to design a scanner. And scanner is the tokenizer. Okay. So here we talk about if there is a language called calculator, and then how you do pre-processing before you do tokenization. Okay. So remove comments. Okay, deal with pragmas, sometimes significant comments. Okay, that may bring in packages to help your tokenization. Okay, so then that's actually the pre-processing part. And then you do work on it. You can design a handwritten scanner to process one character at a time. Okay, process one data at a time to fit it in. So here talk about how ad hoc scanner can be designed. So then you create the labels. Here we call label is actually a AI term. It's not a programming language term. So this actually you create some grammatical units. Okay, classification of the IDs. Okay, you can call it in the programming language like that. AI we call it labels. Okay, you started to labeling on the words as well. Okay, so you actually can design a ad hoc scanner. That means that you do hard coding. Okay, and you can also use a machine generated scanner that actually is using the tools. So design of the scanner, you can use handcraft tokenizer, or you can using the DFA, designing the DFA and then design a systematical converter. Okay. So ad hoc scanner. So here is a figure from the textbook. This one is a programming language pragmatic textbook, and talking about the pseudocode for the hard AHAB scanner, how that can be done. And then you can also design the DFA, okay, and actually deterministic finance state machine to actually convert it to NDFA. I'm sorry, from NDFA to DFA. And then from DFA, you can do systematical generation of the tokenizer. So here you define everything into the finite automata. Okay. And then that actually supported your lexical rule in the tokenizer. So here we do have one example called let's scan.py. Okay. That actually define as in Python that you can do implementation for the tokenizer. So you have the token type, okay, the token types. So this is one dictionary that for the token type, okay. So you have a file name and then input string, okay, and then you are going to create the state variable for the DFA. So state variable means where you are in the final state machine, okay. So you see some number, okay, you go to numbers, okay. You see some parentheses, you go to the parentheses. So the different state, okay. And then you have the tokens and token types. Okay, these are the output string that you create. Okay, output string that you create. And then there's a token that actually is a temporary buffer. So you look at a parenthesis, okay, and then you deliver, you actually tokenize as a parenthesis. Then you may see 2, 3, 4. Then this 2, 3, 4 is put into the token buffer. Okay, let's say token buffer, and later you create a number token. Okay, you create number token, label as token. So label as number tokens. Okay, so here actually give you the whole program structure. You input a file name, you open the file, and then you read and strip using the cleanup. Okay. And then you actually determine the different variable, system variable in the lexical analysis. Okay. And then you go into the scanner's main loop. Okay, so main loop, we just take part of the picture. That this one actually is a partial design for this one. Okay, which I look at emphasize on those part. So this part actually is looking at when you have division. If you have two division, then that is comments. So you're going to avoiding the comments. This one is comment. If you have a slice and then star, you look into the block comments. Okay, but sometimes division is not, division mark is not comments. It's also may not be comments. It may be by itself is a slash. Then that we consider as a single slash division label, and then state 2 finish. So when you have a 2 circle, means that your tokenization finish. Okay, we have a token called division token. Okay. So you see a slash, it may be part of the comments, maybe it's the division mark, maybe it's a block comments starting label. Okay, so these are what this table really say. Okay, so that is the code in Python to look at it. Okay. So that is when you see a slash. Okay, second part, we talk about this part. If you have the operator symbols or parentheses. And these are the code to deal with them, okay? So now we look at if you look at this part, and we look at this 4, 5, okay. Well, what will you get? Okay. And now we look at the lower part. If you see these for assignment and dot, okay, and numbers and letters, okay, how you deal with it. So these are when you see the dot, okay, different functions. Okay, so anyway, this file is a code to actually convert your input ADA calculator language, okay, calculator language, convert it into a stream of tokens and token types. Okay, so these are omitted, and then this is A, and then this is assign, this is number. Okay, so these are the token types that you get. And your tokens are here. These are the tokens. Okay, so that Python program is doing for that. And here another program that's called beta calculator. This is a calculator language. And then the tokens here, your token types here. So basically that one show you how a AHOC scanner should be, okay? Okay, next one is that, okay, sometimes AHOC is not enough because AHOC do come with some problem, okay? As we say, the code words sometimes cannot work because you do split, you'll be being mixed together. So if you have say Hewlett Packard, dash Packard, so by the split you actually consider it's one word, but sometimes you may consider it's two words. So just by split may not be enough. So you need to do some sort of regular expression for systematically designing the tokenizer. So this part gives you the idea of when you have an input file, you actually design your syntax or your lexical rules, or sometimes your syntax. And then based on the syntax rule, you create a final state machine, and that is state machine or a DFA. So your language got qualified by the DAA and generating the token tree, okay, syntax tree. And then based on the syntax tree, you generate the packet code, machine code, or whatever. So these are the grammatical chart for a compiler. Okay. So here we talk about what is the regular language. Based on regular language, you can design regular expression rules. Okay. So here talk about what is a digit, what is an option, what is a clean start. Okay. This clean start means 0 or more. So these are basic definition for the regular language. And you use the regular language to define your lexical rules. Okay, and you based on your lexical rule to design your state machines. Okay, so here give you the idea of what is context-free language. Okay, context-free language actually is a little bit more complicated than the regular language. So regular language is for tokenization or scanner, and context-free language is for compiler. Okay, for the syntax tree for the parsing. Okay, so here define the basic definition for the context-free grammar. Okay. So expression is a special pattern, okay? We call it expression. And grammar is a set of the rules. Okay, language is all the composition of the symbol sequence. So we do have regular expression means that the expression definition of the regular expression. We also may have regular language means that it is the language that do composition of sequence. Okay, and that actually is a regular grammar. So expression, grammar, and language. This is a three-in-one combination. Okay, that means you have the language, grammar, okay, and finite state machine. These are actually sometimes one same thing. Okay, it's three-in-one. A regular expression would define a regular language. Okay, and it's a set of regular grammar. So here is three ways of specifying the regular language. You can use a regular expression, you can use a regular grammar, you can use a finite state machine. They all use to define your regular language. Okay. Any questions so far? Any questions so far? No? Okay. So you define your regular expression, okay, or your regular language in the regular expression, and then you based on your regular expression, you can write a name.latex. That is the latest tool to design the regular expression. And then based on the rule, you can generate a program that interpret the lexical rules. Okay, so this we call it the so-called Flex software or Lex software. Lex sometimes called Lex, sometimes called Flex. Flex is a Windows version software. Okay, so that creating the YYLex function. And then you can also define the syntax rule in the content-free grammar, okay, and then feed into the software of Bison, and Bison can generate the parser code for you. It's called YY parser. So combining the YY text and YY parse, you can actually automatically generate your compiler. Okay. So here, what we want to emphasize on is that you can use a regular expression to generate your table-driven lexical analysis. Okay, unit. So then next one, you talk about what is automata and the relationship with scanner. Okay, so here define what is, here it says three-in-one is a regular expression, grammar, and the automata. Okay, machine, okay. So this one is the regular expression, this one is grammar, this one is the finite state machine. So these are three-in-one. We actually talked about it before. Okay. Three-in-one. You can define one of the way and convert it to the other. Okay. It's finite automata. So here more mathematical definition. Okay. And then this one is your regular expression can also be written in the Baker's norm form. Okay. So this is syntax diagram view. So the same finite state machine can be written down in graph, can be written in this kind of expression, can be written down in grammar rules. It can also be written down as a Baker's norm form. Okay. And Baker's norm form can be written down in such a grammar rules. This is Baker's norm form, okay? And then you can define your language different terms. Okay, these are different terms that you have. Then next one is that you use the regular expression and then it will be converted to a non-deterministic finite state machine. That's a Skinner part two. So here show you how to do the conversion. Okay, how your regular expression converted to finite state machine, converted to grammar rule, converted to the state machine. Okay, so these are can be systematically done. Okay. So here show you the steps of converting from regular expression to the finite state machine. Okay, these are a lot of detail you need to study. Okay, so that show you how the conversion are. Okay, and then here talking about you got a grammar how you do state transition, and then you do optimization for it. Okay, combining the state into a different machine that create the same thing. So finally, you reach the deterministic finite state machine design. Okay, based on your regular expression. Okay, next one is that when you have epsilon, okay, no symbol term, how you actually do the conversion. Okay, so that eventually show you the minimization to reduce the number of state. Okay, and then you reach the final result that you have. Okay, from a 7-state finite state machine to 4-state finite state machine. And then based on the finite state machine, you do scalar design coding part. Okay. So here is the detail of the coding part. We do give you this example so you can study it, okay, the Python code you can and then that's actually ad hoc coding. Okay, and then you can also do table-driven coding that actually is by the regular expression and by the tool. Okay, by the tool. So here show you how the table-driven scanner is. Again, this one is a pseudocode in the textbook talking about how the scanner can be designed. Okay. Okay, again, using the calculator language example. Then here is the final state machine that you got. Okay, you get the table-driven state machine transition. So your state machine, your input, your next state. Okay. And next one, we talk about the extended Baker's norm, how to write the extended norm. Okay, so this one is used for the lexical generator. Okay, so you need to know about the language, how the different term being defined, and then you draw the syntax diagram first. Your grammar, you draw the, and then this syntax diagram can be converted to regular expression very easy. And the next one, we talk about regular expression. What is regular expression syntax? Okay, this example is in JavaScript. Okay, there's one JavaScript example of how to write the JavaScript regular expression rules. Okay, there are quite a lot of information. You should study. Okay, and then okay, still in the JavaScript part. So you can use the regular expression in your program to qualify your input tokens. Okay, and you can also use tool online to do it. Okay, some of the editor also have the regular expression option that you can choose. Okay, so this one we actually working on a tokenizer Okay, we talk about how is the grammar of the tokenizer and how we do tokenization. And we also give you the ad hoc tokenizer code. We also give you a table-driven tokenizers steps, okay, and how it is done. Okay, so this one is the part one for tokenization. Next week, we'll talk about the part two of the tokenization, okay, using the tool, the Flex tools, okay? Any questions so far?
I'm good.
Okay, no question, that's it for today, okay? See you next time, bye-bye.